Okay, so this session we want to start generalizing more some of the old concepts that we learned before. One of these concepts are the union, intersection, and we will introduce a new concept called the index family of classes. But like the aim is to rely less on intuition and rely more on mathematics and logic. And this entails that we need to generalize a little bit our formal definition of what a union is or what an intersection is, etc. Okay, so in order to do this, we will develop a concept. It's called the index family of classes. So the index family of classes has some features or some key things that whenever you see, you know that you are dealing with an index family of classes. So first, you have the class of indices. So we'll just denote it with I. So the class of indices is just like it's just the class of all of every single index, or the class that contains every single index in it. Okay. This C would be the index family of classes. So it would be A sub I, A sub J, A sub K, where I, J, K are some of the indices, or I, J, and K belong to the index of the indices class, right? And I, J, and K are just some arbitrary letters, so they can be replaced with numbers or with anything. So you can have instead of I, J, and K like 0, 1, 2, or whatever. So I, J, and K are just arbitrary numbers, and they represent any index or any subscript in general. This is just a different notation for the same thing here. So I can say that C equals the class of A sub I, such that I belongs to this to I. So here you have the small I and capital I, of course. So this is just another notation where you say that this is the class of all of A sub every single index, right? So this is just the same as here because I would be just any element that belongs to the class of I, right? So it can be I, J, K, or any other one of the indices that are used. So there's just a shorter notation. So instead of listing every single class that you have, you can just put it in this shorter form, and so it will be easier. But even though this definition would work fine, it's still intuitional because we did not really develop what does an index mean. So the within our the set theory that we have been dealing with, we do not develop the concept of index really. And so in order to avoid this additional definition or this undefined notion of index, we need to define it formally in terms of set theory, in terms of terms that we already defined in the axiomatic set theory, right? So in general, as we are developing a whole new system in set theory, we need to ignore any other intuition or any other definitions outside the system because this is really the foundational system. So it would not really make sense to make the foundational system rely on another notion or another predefined notion from another system because then it will not really be foundational. So in order to do this, we define the index family of classes in terms of a graph. So I can say that the index family of classes is the graph of domain I. So I is just in the previous is just the class of all indices. So I can say that uh, the index family of classes is just a graph with domain I, such that you have that a sub I equals x, such that I and x belong to G. So what this just means, if you remember in graphs in the last session, we talked about that it has something called the domain of the codomain. So the domain was just the first element in the ordered pair, I and x. So when I say that this belongs to G, I'm just saying that the domain of G is I. So this is just the first part, and A sub I would resemble all the x such that they resemble the codomain. So this is just similar to this will get the very same results as the older definition, but the difference is that the older definition is just intuitional. So this definition relies on intuition and the notion of index, which was not really defined within set theory. However, this is just we can think of index family of classes as nothing but graph. So I don't really need a new undefined notion, or I do not need to introduce a new undefined notion. So here's an example. If I have I equals the class of 1 and 2, I have A sub 1 equals H and B, and A sub 2 equals C and D. So now I have the class of indices. I have A sub 1 and A sub 2. And so through these, I can know what the index family of classes is equal to. So the index family of classes is just the graph with the domain of the I. So I have 1 and 2, so this would be my domain. So whatever in the first place of the ordered pair would be either 1 or 2. And I have the H, B, C, and D are my codomain. So whatever in the second place of the ordered pair would be either H, B, C, or D. When I say A sub 1, I mean that H and B would deal with the domain of 1, right? So the overall would be that G equals the class of these ordered pairs, 1 and H and 1 and B, 2 and C and 2 and D. So this is just, if you just think of it, you find that I'm taking A sub 1, so I take 1 as my domain. So I take 1 as the first part of the ordered pair. And then I take H once as the Y, or the second part of the ordered pair, and B as the second part of the ordered pair. And this can be applied in general to any number of indices and any number of classes, actually. So the aim of all this is just, instead of defining classes as A, B, C, and D, the class A, the class B, the class C, I can use just one letter, just like A, and based on that, I can have literally an infinite number of classes. I can always represent A sub some number or some letter. So instead of saying class A and class B, I can just use the letter A and resemble all the possible classes that I would need. So this is just how we deal with index family of classes. We are just defining a graph, and so by defining this graph, I can define an infinite number of classes, actually. So based on this new notion of the index family of classes, I can start having a more general definition of what I mean by union and intersection. So in the last sessions, we spoke of union. Just A union B means that all the elements that belong to either A or B, and for the intersection A intersection B, I just spoke of it as any element that belongs to both A and B at the same time. But I want to generalize this concept to any number of sets, any number of classes. So this is just a very long notation, so I'll just go through it step by step. Or this is just saying that the union over all the classes A sub I. So I'm just taking all the classes with a certain index. So now I still have my indices class, and I'm just taking A sub I, A sub K, A sub J, etc. Right? So I'm saying that the union is equal to X, such that there exists a J belonging to I, such that X belongs to A sub J. So what this is really saying is that the union is just all X's, such that at least X belongs to one of the classes with a certain index. So all of what this is saying is that X belongs to at least one of these classes, which is just the same definition of union we used before. So when we defined A union B, we said that X has to belong to any of these two, to at least one of them. Right? It can belong to both, but it has to belong to at least one of them. So this is just the same. I'm saying that the union of the union taken over I of A sub I, so of all the classes, well, with the indices class, is just X such that there exists a J belonging to I. So J belonging to I is just one of the indices, one of the many indices that I can have. I have that X belongs to at least one of these. So this is just what a union is. So this is just the general definition of a union, and you can see that our older definition is a special case of this definition. Like in the case of A union B, you can think of B as just, instead of A and B, you can think of A sub 1 and B sub 2, and A sub 2, sorry, and you can just apply the same definition. You'll find that it yields the same result, actually. Same thing for intersection. So I can say that taking the intersection over the classes of all the classes of some sort of index that belongs to I is just X, such that for all J belonging to I, X belongs to A sub J. So what this is saying that to take the intersection over a number of classes, let's call them A sub I, where I of course varies through all the indices. So I here is just an arbitrary variable that can be I, J, K, or any one of all the elements on the indices class. So this is just saying that it belongs to every single one of these, right? So here, the notation that we're using, like the small I and capital I, you can see that it's analogous to the one we are used to in natural numbers. So in general, in arithmetic, when we used to generalize a rule, we said that for all n small belongs to n capital. So n capital resembled the natural numbers, and n small resembled any number that we are dealing with. And that's just using the same notation. We are using here I small to resemble anyone that belongs to the class of I, capital I. Capital I just resembles the indices class. So just using the same idea that we use in arithmetic when we use, for example, general rules that apply to all natural numbers or to all integer numbers or whatever. So again, also this intersection is similar to our older definition, or it's the more general form of the older definition. So if you had A intersection B, we said that this means all the elements that belong to both A and B at the same time. So I'm here saying the same. I'm saying that taking the intersection over all A sub I, it means that X belongs to A sub I for all I. So whatever element you find in the index logs, so whether A1, A2, or A3 or whatever, it has to belong to all of them in order to belong to the intersection. So this is just again this this is you can say that our older definition A intersection B is just a special case of this general rule. So I hope that this idea makes sense up until now. So in order to check that our rules still apply, and indeed they would apply here. So the same rules that we used to apply to the older definition of union and intersection would apply to this more general definition. So De Morgan laws, if you remember them, it said that A union B all dash is just A dash intersection B dash, and this applies here. So if I take all the union and take its complement or all the union dash, this would give me the intersection of A dash sub I. So and the same thing, of course, for the intersection. If I take the intersection where I varies over the all indices in the class I, of if I take the dash of all this would equal to the union of A dash sub I. So we are not going to prove the second statement, we're only going to prove the first. And the proof of the second should be very similar actually to the first. So there will not be much a great difference between these two. So we'll try proving the first. So first, if I have X belongs to so the union all dash. So in order to proceed or in order to solve that kind of proof problems, you can think of it in two ways. Just plugging in the definition, or you can say, what is this telling me? So when I look and say that X belongs to whatever class is here, dash, or this is telling me that X does not belong to this class. So this is just what this means, actually. So X belongs to the union of I belongs to I of A sub I. All dash means that X does not belong to the union as I varies over the class of all indices of A sub I. So again, you can still further ask what this means or what is this telling me. So I can just plug the older definition we had for the union. So now I know that for all I belongs to I, X does not belong to A sub I. So from where I know this, because I know that if X belongs to just any one of the indices of A sub I, so if it belongs to A sub 1 or A sub 2, or actually any one of these classes, then it would belong to the union. But I know that it does not belong to the union. Then I know that it belongs to none of all the indices. I know that it certainly does not belong to any of the classes that I'm dealing with. Because if it belongs to at least one of these, then it would belong to the union. So when I say it does not belong to the union, then I mean that for all the indices that I have, X does not belong to A sub I, to any of these indices. So again, I can ask, what is this telling me? I know that if X does not belong to A sub I, then X belongs to A dash sub I. So this is plugging in the definition of what the complement means or what A dash means. So so this just would translate as the second one. So for all I belongs to I, X belongs to A dash sub I. And this is actually what the intersection means. So if I go back to the definition of the intersection, I know that it means that X such that for all J belongs to I, X belongs to A sub J, right? So by replacing here A sub J by A dash sub J, I can reach my conclusion, just that for all I belongs to I, X belongs to A dash sub I, and I know that X belongs to the intersection over A dash sub I. So I'm going to go through this proof once more because I think it might be a little complicated. So if I have an element X belongs to this right here, so if I have an element X belonging to the complement of taking the union of all the clauses of indices a sub I, right? So so again, you should remember that this just means that you are having a large number of clauses, like any amount number of clauses, and you're taking their union, right? So if I take the dash of all of that, I know that X does not belong to this union. But if X does not belong to the union, then it surely does not belong to any of these A sub I, because this is just the definition of union. Even in the case of A union B, if I know that X does not belong to A union B, then I know that X does not belong to A and X does not belong to B. It cannot belong to any of these, because in the case of it belonging to any of them, then it will belong to the union. So this statement right here, that the fact that X does not belong to the union, implies that for all I belong to I, X does not belong to A sub I. So that this just means that X does not belong to any of the classes that I have, because if it belongs to at least one, then it would belong to the union actually. So here I'm just using, then I will use the definition of dash or complement. Then I can have that for all I belongs to I, X belongs to A dash I. So I know this just because X does not belong to A sub I, then X belongs to A dash sub I. So this is just the definition of what it means to take A dash. And this is just the definition of the intersection. That for every single index I, X belongs to A dash I. So this is just the intersection of all the A dashes that I have. So what this statement is saying, that for any index that you put, so if you put A sub 1, A sub 2, or A sub 0, for, or any number actually, or any other index. So for all these indices, you'll find X in the A dash, right? So this just means that it belongs to the intersection. It belongs to all of them at the same time, which is just the definition of what intersection means actually. So as De Morgan laws actually apply to our new definitions, so do the distributive laws that we learned in the former definitions of union and intersection. So what this means, that if I have that the union of I belongs to I of A sub I, intersection the union of J belongs to J of B sub J, again, you can, these are just an arbitrary index family of clauses, and this is also the same, an arbitrary index family of clauses. Then I would have that this would be equivalent to the union taken over ij cross belongs to I cross j, and this just means that I belongs to I and j belongs to j, because if you remember in the when we deal with Cartesian products, if I have AB belongs to A cross B, then I have that A belongs to A and B belongs to B. So I take the first member of the ordered pair, and it belongs to the first member of the first clause that is being that's in the Cartesian product, and the second element in the ordered pair just belongs to the J here, or to the second clause in the Cartesian product. So this is just saying that I belongs to I and J belongs to J. So it's just the same condition we started with. So I take the union of A sub I intersection B sub J. The same thing applies for the intersection. I can take the intersection of I belongs to I, A sub I, union the intersection of J belongs to J of B sub J. So this would be just equivalent to the intersection taken over the ordered pair of I, J belonging to I cross J, or the Cartesian product of I and J of A sub I union B sub J. So again, as in the previous case, we are going to prove the first statement, and the proof of the second statement just applying the same logic or the same idea. So just before I proceed to the proof, I will just restate what the law says in order to make sure that it's just clear. So if you are taking the union of certain classes, so of a certain index of classes, a number of classes, let's call them just A sub I, okay? And you're taking the union of another group of classes, let's call them B sub J, and you want to find the intersection of these two unions. So what this law said, that it's equivalent to the union of the intersection of these two. So if I take every A sub I and intersect it with every P sub J and take the union of all of these, this will give me the same result. And the same thing goes for the second statement. So in order to proceed to proof, we proceed as usual. I say let X belong to the union of I belong to I of A sub I intersection, the union taken over J belong to J of P sub J. This should have been J. So what this is telling me, that since it belongs to the intersection, so So I'm going to plug in what the intersection means. This means that X belongs to the union of I belonging to I of A sub I, and X belongs to the union taken over J as it varies over the class of J of P sub J. So this is just transforming the intersection into the AND form. So if something belongs to the intersection of two classes, then it belongs to the two classes at the same time. So here I'm saying that X belongs to this class and that X belongs to this class also. So then I can start plugging in the definition of the union, right? So I'm saying that from the definition of the union, I can say that X belongs to A sub H, where H is just any arbitrary index that belongs to I, right? So H is just any of the many indices that belong to the class of all indices. So I can say that X belongs to A sub H and X belongs to P sub K, where K just belongs to J. So of course here H and K are just some arbitrary indices that belong to each of these belong to the certain class of indices that resembles the class that we're talking about. So for example here A sub H, so I know that the domain of A is over I, right? So now I can say that H belongs to I. So H is just any of the many indices in the class of all indices. And the same thing goes for the second case where we're dealing with B sub K. So I can say that K belongs to J, where J is just the domain of that graph or that index family of classes. Because I can now think of K just as part of the domain that we are dealing with. If we go to the graph definition of the index family of classes. So then proceeding further, I can say that X belongs to A sub H intersection P sub K, because since X belongs to A sub H and X belongs to P sub K, then X must belong to the intersection. Now, this new thing where I say that the ordered pair of H and K belongs to I cross J, it's just the same as saying that H belongs to I and that K belongs to J. So that I did not change any of the conditions that I started with. I started with the condition that H belongs to I and K belongs to J, and here I have the same thing. If I have the ordered pair of H and K belonging to I cross J, then H belongs to I and K belongs to J. So that's just the definition of a Cartesian product, actually. And so that actually close proves the theorem that I'm trying to prove. I can say that this close proof that X belongs to the union taken of over I, the ordered pair of I and J, which belongs to I cross J, of A sub I intersection P sub J. So from where I can find this, because what this statement is saying is that X belongs to A sub H intersection P sub K, such that there exists that ordered pair H and K that belongs to I cross J. So that's just, again, the definition of the union that we used before. So the whole idea is just in substituting for classes, by understanding that A sub H and intersection B sub K is just in itself a class that can be represented differently. So I can just plug in the definition of the union back and substitute back using this new class in the definition of the union. So I know that these new notions might be a little complicated, but like, especially these parts of set theory, they come with practice and looking at a lot of proofs and proceeding and solving a lot of proof questions. So even if this does not seem fully clear at first, it gets easier over time actually. But I hope that up until now, like, the whole idea is clear. Okay, so we can proceed further into the further concepts. So now we'll speak about sets and proper classes. So in all the previous sessions, we spoke about operations on classes. So we spoke a class union a class and a class intersection a class. And actually that would not differ in while dealing with sets. The same rules that we spoke about or that we proved while dealing with classes applies to the sets actually. So but still for the future we would need to draw a distinction of two kinds of classes. So sets and proper classes. So these are two different types of classes. So sets are classes and proper classes are classes, but they are different kinds of classes, okay? So the difference is that if you have X belongs to Y So you have y as a class and you have x belongs to y, then x is called a set. Okay. If you have that x does not belong to y for any y at all, then x is called a proper class. So simply you can think of it that a proper class is a class that does not belong to anything, whereas a set is a class that can belong to some class or another, right? And this actually in axiomatic set theory that requires us to equate sets and elements. So whenever I say set or an element, these two are actually synonymous. I can use any of these two and they mean actually the same thing, set or element. So all sets are elements and all elements are sets actually. So the distinction between sets and classes, you can think of it that classes are just very big that they cannot be included in anything. Right? So you cannot have that. You cannot. There exists no class such that the proper class is belongs to it. So, that if you have x does not belong to y for all y, where y is just classes, y represents classes, then x is called a proper class. So a proper class is just simply any class that does not belong to any other class, whereas a set is a class that belongs to some class or another. So that is the distinction between a class and a set or an element. So we can So we need some axioms. So in case you do not remember what an axiom is just the basic facts on which we build all our system, right? So axioms are just almost like the accepted tautologies or the things that don't really require a proof but are just assumed to be true or accepted to be true. And based on these axioms, we will build the whole system of the set theory that we're dealing with. So the first axiom is that every subclass of a set is a set. So if you have a certain set and you have any class that's a subclass of it, then that would be a set also. So for example, if you have A is a set and you have B subclass is a subclass of A, then B is a set also. So this just guarantees that if you have a certain set, then you know that all the elements inside it are sets, that they cannot be proper classes. Based on that, you can actually conclude that A intersection B is a set if A or B is a set. So from where we conclude this, because I think we have proven this in the very first sessions that A intersection B is a subclass of A, and that A intersection B is a subclass of B. Because if there exists an element that belongs to both A and B, then it certainly belongs to A, and it certainly belongs to B. Then you can say that A intersection B is actually a subclass of A, or that A intersection B is a subclass of B. And so if I have A is a set, and A intersection B is a subclass of A, then A intersection B must be also a set. So you can notice that we are starting with a set, and based on that set, we can define many other sets, right? So if I just have A and B are sets, then I already have a new set which is A intersection B, and I can say that this is indeed a set with a proper class, etc. The second axiom is that the empty set is a set. So the empty set can be written in as the simple phi. So the second axiom that we'll be dealing with, that phi is a set or the empty set is a set. So this already guarantees the existence of a set or another, because even if you read the first axiom, you'll find that every subclass of a set is a set, but this does not guarantee the existence of any set at all, because it might be the case that there are no sets and everything are just proper classes. And so this guarantees that there exists at least one set, which would be called phi, or the empty set. So this already guarantees that we can deal with sets, and based on that, we'll actually build many sets in the future. So the third axiom would be that if you have A and B are sets, then the double of the class of A and B is a set. So if you have A is just any arbitrary set and B just any arbitrary set, then the class of these two, while dealing with A and B as its elements, would be a set. And actually, the same thing applies to singletons. If you have A as a set, then the class of A would also be a set. You can already notice that the existence of one set already guarantees the existence of many other sets. And that's the whole point behind axiomatic set theory, that you start with just a set or two sets, and based on these sets, you start building the whole system. And we'll actually use this fact a lot while building the natural numbers and many things in more advanced parts of set theory. Then now we'll start constructing sets. We will have the concept of starting with a set, and based on that set, we will build many other sets. So if you look here, we first have phi as a set. We know from the third axiom that the class of phi would be also a set, right? So that's just from that axiom. If you have A as a set, then that's a set. And you have that phi of the empty set is a set, right? Then I know that the class of the empty set would be also a set. So now I have a new class. But then, since I have the class of phi is a set, and I have phi as a set, then I have that class would be also a set. That is the class of phi and the class of phi. So I'm just starting with phi, and then I build a new set, the class of phi. Based on these two together, I can build the class of phi and the class of phi. So, and then combining these two together, I can build this new class with the elements phi, the class of phi, and the class of phi and the class of phi. So actually, reading it might make it harder, but like if you just look at it and if you just don't really read it aloud, it might feel a little easier to decipher or to understand what it actually is saying. And actually, this concept is a very powerful concept because based on these of the empty class, we will actually build the whole system of natural numbers, and we'll build addition and subtraction, multiplication. All of these will be based on this concept, but that's still a more advanced topic that we still did not reach. So, so these are just how we define our notation. So, yeah, you have these curly brackets. So the everything that's inside it are the elements of the class or the elements of the sets, right? The comma separates each of these elements. So this comma indicates that this is a separate element from that one. This comma indicates that all of that is a separate element from this one, etc. So there are many notations to represent set, but one of the most famous or the most one that we'll be using is the set builder notation. So for example, if you want to represent the set of all even numbers, you can say that x, such that x equals to n, where n belongs to n. Okay. So what the whole idea is just that you write here, this represents all the elements that you have, and then you separate the variable from the condition by these two dots, right? So I'm just saying that this would be all the elements x that apply to this rule. So this is the set builder notation, and I think we already use it a lot in a lot of our discussion through the last sessions. We use this notation a lot where we just put this element x, and we say that this would contain all elements x that admit to this rule. And actually, if you go back to definitions, you'll find that we use this notation here also. So this is just saying all elements x that admit to the following rule, etc. So this notation is really helpful in deciding what elements actually exist inside the set or inside the class. So one last important concept that's really actually powerful and that would contribute in a lot of theorems in future classes would be the power sets. So the power sets denoted by P of A is just all the classes B such that B is a subclass of A. So in English language, this would translate as if you have a class, then the power set of this, or if you have a set, then the power set of it would be all the subsets of this thing. So it's just the set of all the possible subsets that you can get out of this class. So for example, if you have A equals A and B, and you want to find the power set of A, then this is just phi, the set of A, the set of B, and the set of A and B. So why is this true? First, we know that phi is a subset of any set, or phi is a subclass of any class. So the power set, since the power set is just all the subclasses of A, so the power set of A is just the set of all the subsets or the subclasses of A, then I have that first, since phi is a subset of any set including A, then phi is included, the set of A, the set of B, and the set of A and B at the same time. So this is just the positive thing. And this applies to any number of elements actually. So even if you had many more elements, more than two, it's not restricted to a certain number of elements. The same idea applies to the positive thing. And you would actually notice that the one common thing that you find that phi is always a subset of the set, and every set is a subset of itself. So A is a subset of A actually. So so that's why you will find that here the whole set of A is included, and you'll find that phi is also included. And that's something that you'll find in any class or any set that you're dealing with. So these are some exercises that you're supposed to try and solve. So like try finding the answer to this and type it in the chat. Okay, so the answer would be that the process of A would be phi, the class of x, the class of y, the class of z, and then the every combination of the two of these x, y, y, z, x, z, and x, y, and z all together. So this would just be give me the whole set of A. So using the set builder and notation, describe the set of all odd counting numbers. So the question here is asking you to write a class, to write the class in the form of the set builder notation that would include all the odd numbers. So all the even numbers with two n's. So try representing all the odd numbers this time. Now again, also type the answer in the chat once you finish. Okay, so the set of all odd counting numbers would be x, so that x equals 2n minus 1, where n belongs to n. So this would resemble all the set of all odd counting numbers in the notation. So that's it for today. So if you have any questions, so feel free to ask.